One thing about these roadmaps that I do not necessarily to challenge, but to remind you that there are different ways of communicating things. Look at that starting material. It's got a benzene ring with an alkyne coming off of it, a terminal alkyne. And then the product that's given after it, on your version, I show the aromatic ring, and then I show the carboxylic acid as CO2H, which means you still have to be able to interpret what does that CO2H mean. Well, as we move to the left, we actually cleave a carbon. I have 2 carbons of the alkyne off of the aromatic ring. And in the product, I've only got 1 carbon. So where did that other carbon go? It must have been cleaved. How many ways can I cleave an alkyne? 1 way, oxidative cleavage. Oxidative ozonolysis or hot potassium permanganate will also do this same cleavage for us. As I take that alkyne and I react it with mercury sulfate in sulfuric acid, what functional group do we predict from the oxymercuration of an alkyne? No. We predict a carboxylic acid forms from the oxidative cleavage, but from the oxymercuration. Now, this is where I recommend using these diagrams. Every semester that I've taught this class, I also recommend that outside of class, you build a table of reactions. And I have given you all of the reactions that I would recommend putting into the table. I recommend organizing this table as your starting materials functional groups, like all of the alkyne reactions that we've learned, and then your products functional group. In this case, when we do oxymercuration, the functional group that we predict is a ketone. Now, in this table, if you take the time to build a table like this, you might put notes in here, like how this is a Markovnikov addition. I started doing this when I started OCHEM 2 because I realized how many reactions from OCHEM 1 we had learned, and I didn't remember. And I actually made mine on an Excel spreadsheet, and I organized it just like this. And later, I don't know that it was the best way to do it. Students of mine in the past have done this by hand. Students have done it on a Word document. Students have done it on a tablet so they can actually like insert space and keep building it. I've seen students that incorporate mechanisms into each line so that they can understand what change is happening by the mechanism. If you spend time building a table like this, especially if you leverage what's already been given to you about what reactions you need to know, it takes a ton of time. And all of that time is time spent studying. By doing it by hand, you actually use all those fine motor skills that lock it into your brain better. So do it by hand. And then take the ones that you really struggle with and put them onto your cheat sheet. Take some of them with you. Okay, so what functional group is formed by oxymercuration? A ketone. This is Markovnikov hydration. Hydrogen added to the carbon with less hydrogen, and the carbonyl formed on the more substituted carbon. If I deprotonate my terminal alkyne, and then I introduce it to this carbon group, what I like to show is I map my carbons to show the nucleophilic attack. So I've got the aromatic ring, carbon 1, carbon 2, carbon 1, carbon 2, carbon 3. Carbon 3 attacks the electrophile, the alkyl halide. So 3 attacks 4, 4, 5, 6. And here I've got 1, 2, 3, 4, 5, 6. Great work. Mapping your carbons can make it that much easier to actually know what the structure should look like in the end. I'm not going to lie, this one in green, it shows it the way a chemical software structure would show it. You see how it's that one long line? That's not usually how I draw my alkynes. And the only reason that I would recommend drawing it the way that I do, the difference being I draw my 3 lines of the alkyne as each a short little burst. The only reason I do it that way, or the reason I'd recommend it, you can clearly see the break. You can see exactly where the carbons are. And this is the struggle that I think a lot of you have when you see it on a software drawing, is that that one through line can make it kind of hard to interpret how many carbons are actually there. What am I looking at? This reaction is called what? It is substitution, and it's alkylation. Alkylation of the alkyne. Okay, to get from the alkyne to an alkene, H2 with Lindlar's catalyst, or because we're not going to a cis or a trans alkene, I could have also used sodium in ammonia. It would have worked just as well here. So there are 2 correct answers for this one. From this alkene, hydroboration, halohydrin addition gives us a less substituted halo, a more substituted alcohol. HCl gives us Markovnikov addition. The chlorine goes to the more substituted carbon because that's where the carbocation goes. This one, we are looking at an anti-Markovnikov HX addition. So X2 will not complete the reaction as shown. X2 would add 2 halogens, 1 at each position. What do we want instead in that last box? HCl would give us this, though. So we know it's not HCl, even just from the context of what's already shown. We want HCl and H2O2, not H2O. Did you say H2O? H2O2, or just in general, peroxide, ROOR. It's one of the few times I really am okay with you just writing ROOR, because it doesn't matter what those R groups are. They could be hydrogen, they could be tert-butyl, they could be methyls. It's the peroxide that gives us our radicals. Okay, by the way, if you can name each of these reactions, you're in a good spot. If you can't name them, that's a skill to practice. Look at reactions until you can name all of them. The other roadmap, let's start here with our alkene. I want to go from an alkene to a vicinal dihalide. I want bromine for that. Earlier, we had seen the alkene, and then someone had written halogen with 1 equivalence. First of all, I would have wanted to know what halogen, because it is specific. And we don't have to specify how many equivalences with an alkene, because an alkene can only do 1 addition. Alkynes, we have to specify the equivalences. It's not wrong. If you put Br2 1 equivalence, it wouldn't be wrong. Even if you put Br2 2 equivalences, the excess can't do anything different, but we don't have to specify it. We just need Br2. Now, what change do you see happening in this next step? A vicinal dihalide becomes an alkyne with a longer carbon chain.
So that's like the substitution alkylation of an alkene to an alkyne?
I would say it's a little bit more than just alkylation. It's both synthesis of the alkyne and alkylation combined over 1 arrow, which means that we're going to need to show multiple steps, 1, 2. So it's evidence that we've alkylated because we have a longer carbon chain. And there's evidence of forming the alkyne, because obviously there was no alkyne before. So first, let's form the alkyne. We'll use our strong base, and let's use enough equivalences of it that it fully eliminates, forms the alkyne, and deprotonates. Remember that this first step is essentially going to be doing one elimination, doing a second elimination, and then deprotonating the alkyne and forming the nucleophilic acetylide ion. Then I want to attack an electrophile. So these were my carbons 1, 2, 3, and 4. And I can see that 4 needs to bond to 5, 5 bonds to 6. 6 just is a benzene ring. So I want a reagent that has carbon 5 with a leaving group, something that can be substituted. So here's 5, here's 6, and I'm going to put a bromine. I could put a chlorine. I could put an iodine. Those are all good leaving groups. So step 2 is Br2, CH2, pH. My substitution step introduces the carbons that I'm missing. What's the difference between what we just did to the right and what we're trying to do going up?
But you're just doing the formation of alkyne without any sort of addition.
Good. We're just going to form the alkyne. We're not doing alkylation. So I could do NaH, 2 equivalences. Your active homework occasionally will say NaH excess followed by H3O+. That just makes sure that in case you overshoot, you can reprotonate and get back to the neutral alkyne. That would be the work backwards. Go too far, take a step back. You don't have to show that if you're filling in a roadmap. You can just say 2 equivalences. In practice, it's maybe more challenging. Okay, let's take that alkyne. What happens with HCl and peroxide? Anti-Markovnikov addition twice. And I know it's anti-Markovnikov because of the peroxide. Once again, map your carbons so that you don't accidentally add carbon chains or remove carbon chains, carbons from your chain. Back down to the right. I'm sorry, maybe I shouldn't have been doing any of this in orange. I know orange can be a tough color to read. Back down to the right, I've got this internal alkyne forming a cis alkene. What reagent completes that conversion? Good. H2 with Lindlar's catalyst. And remember, Lindlar's catalyst is the palladium, but also a barium carbonate quinoline mixture that poisons. It's not. It also has PD.
Yeah, but not.
But it's not just PD. There's a poison in it. All right, what about the alkyne, but 2 equivalences of Br2? I'm sorry, 1 equivalence of Br2. What functional group should I make? This will make an alkene with anti-addition of Br2, which means that on the alkene, the bromines will be trans to each other. If it were 2 equivalences of Br2, then the alkene goes through a subsequent halogenation. We get a tetrahalide. But it's that 1 equivalence that leaves us with an alkene remaining. These are challenging. I completely understand that. Filling in these roadmaps is a challenge. That's the goal. Actually, if you look back on some of my very oldest exams, the way that I had students fill out questions like this was a list of starting materials and reagents, predict the product, and a list of starting material and product, give me the reagent. I find these to be a little bit more of a puzzle and a little bit more fun. The other thing about these, for as intimidating as they can be, you don't have to get everything right to be able to get other stuff right. I can answer this final product without having any idea what reagent needs to go here. So don't let it get you down when one part of it is challenging you and other parts are not. Identify the challenge, focus your studying there. Questions on this?
For Lindler's, would it always have like that cis?
Lindler's hydrogenation, partial hydrogenation, always gives a cis alkene. Okay, I think I've got 5 there.
And if it doesn't, it's Na and NH3.
If you need it to be what type of alkene? Welcome. NaNH3 makes what type of alkene? Cis or trans?
Oh, trans.
Trans alkene.
Oh.
Right. Classic. I'll figure it out one of these days. Oh, wait.
Oh, wait.
Oh, I was short? Sorry.
Oh, I'm sorry, I didn't hear you.
So to follow up on your question, Lindler's catalyst doesn't always make a cis alkene. That's not a cis alkene, is it? Why not? It's terminal. It's missing another group. This carbon has 2 identical groups. And we said that an alkene can only be cis or trans when both carbons have 2 distinct groups. So this alkene can't be cis or trans. So hydrogenation doesn't always make the cis alkene because there's not always a cis alkene to make. When it makes a stereo center, when the alkene is either cis or trans, yes, Lindler's catalyst, always cis. The wrong answer here would have been sodium in ammonia. But this one, either of them would have been the correct answer.
Oh, because it's terminal, so it doesn't matter.
Exactly. This does not make a cis or trans alkene, so I can use either of my partial reductions. This needed to make a cis alkene, so I need the partial reduction.
Right, and that first stereo center is trans and NaNH3.
You got it. All right. Our last packet. And a lot of reactions. So I'm gonna keep things kind of short and sweet as we look over some of these new reactions, and we're gonna try and prioritize getting to the mechanisms, because all of the other practice, you guys can find time next week with Natalie to practice these things. But I want to. The way that I present mechanisms, I've never seen anybody else present. So I want to make sure that I present the mechanisms to you so that Natalie doesn't have to next week. Let's look at our reactions with conjugated dienes. All right, I've asked this a lot. Let's see if you know it now. What does conjugated mean in this context? They're related to each other. What are? Yeah, those 2 alkenes are related. What I want you to see here is that the conjugated system means an uninterrupted series of p orbitals. What's interesting about dienes, especially conjugated dienes, they have two possible carbocations that could form. If we interact these with something like HX, we could add the new hydrogen, anti-Markovnikov. Okay, we know that that's not how it likes to form. Or we could form the new hydrogen Markovnikov. The difference about a normal HX addition and this HX addition one of the possible carbocations has no resonance. The other possible carbocation has allylic resonance, meaning it's not just one carbocation that forms. It's a carbocation split against two positions. So which one reacts? Which resonance form is the one that actually goes through HX addition? Does the halogen add at the secondary carbon or at the primary carbon? It can do both. Isn't that fun? So here's what I'm going to do. I'm going to give you a two-way reaction coordinate to explain why we can do both and how we can control them. If I have this allylic carbocation, meaning I've got it in resonance, it's not necessarily in one spot or the other. If the reaction proceeds by the more substituted carbocation, if the reaction proceeds by the less substituted carbocation, that's a high energy structure because it's a less stable carbocation, but the final product is a more substituted alkene. If the reaction proceeds by the more substituted carbocation, then it forms a less substituted alkene. One of the carbocations requires more energy to form, but creates a more stable final product. And one of the carbocations takes less energy to exist, but also creates a less stable product. We refer to these reactions where two different products are possible with two different transition states and two different final energies. We refer to these as thermodynamic and kinetic. On the right, we have our thermodynamic pathway. I remember this as thermodynamic because it has the highest high and the lowest low. It's the most dynamic. It requires the most energy, but once it's done, it gives you the most stable product. The other method, the other reaction route is the kinetic product. Now, kinetics, you probably are thinking about movement, motion, energy, kinetic energy. And the reason we call it the kinetic product, or what I assume is, this is the product that forms with just enough energy. If you only put in just enough energy to get over the smallest activation barrier, that's the product you form. In my opinion, connecting the name kinetic with that structure it's hard to do. It doesn't make sense to me. But thermodynamic always makes sense. It's the most dynamic product. as long as you can remember one of them, you can remember the other process of elimination. So we see this with HX addition, that we've got two different products, thermodynamic and kinetic. And so we can control which product forms by using temperature. Kinetic control requires us to run this reaction at 78 degrees below 0 Celsius. That is quite literally just enough energy for your molecules to move. It's hardly enough energy for them to do anything else. It is just kinetic energy, lowest activation barrier.
And that's only for halogens? Or
Well, no, you can see it's the same for HX and X2. So halogenation and hydrohalogenation.
okay.
Both of them proceed by the same route. This is the most stable intermediate, but the least stable alkene product. Kinetic control is, we just say with heat, or excuse me, thermodynamic control just uses heat. And this has the least stable intermediate, which is why it requires that heat. But it has the most stable alkene. I'll be honest, my questions on exams about thermodynamic and kinetic products are usually pretty short. And oftentimes, they're not asking you as much about these reactions as it's asking you things other than that, chirality. So it'll use this as an example reaction, but then it'll ask you to describe things about the product, functional groups, chirality, spectroscopy type questions, things like that. There is a relationship between the terms kinetic and thermodynamic with the terms 1,2 addition and 1,4 addition. But unfortunately, they are not always the same thing. So I want you guys to decide on that 4-coordinate roadmap, can you tell which halogenation is 1,2 addition and which halogenation is 1,4 addition? The halogenation that goes up, is that 1,2 addition or is that 1,4 addition?
1, 2.
I agree. 1,2. Because both carbons 1 and 2 got a halogen. And going down the halogenation at thermodynamic control, 1,4, because one adds to carbon 1, the other adds to carbon 4. So you all know the mechanism of halogenation, and you know that it gives an intermediate, the halonium ring. To get the 1,2 addition product, kinetic control, very cold temperatures, we keep it cold, which means that it attacks at the more substituted carbon, and it gives us our 1,2 product. But to see the formation of the thermodynamic product, 1,4 addition, the nucleophile has to attack at position 4 and cause the pi bond to shift before breaking open the ring. This requires more energy, so we run this at a higher temperature. Questions about our reactions with dienes?
So,
Uh-huh.
with like
Yep.
You said that with the kinetic neutral, it's the least stable alkene. So once you have this product, this one would technically be more reactive than if you had gone thermodynamic route.
Sure, yeah. This alkene is more reactive than this alkene, but not by a lot. Not in the same way that, or I guess in the same way that primary carbocation is more reactive, less stable than a secondary carbocation. They're both still reactive. It's not that this is now inhibited from doing alkene addition, and this one's not. It's just that like the energy difference might be, you might need less energy to run this reaction and a little more energy to run this one.
So we said that with kinetic control, it has the most stable intermediate, thermodynamic is least.
Yeah.
But those are, is it discussing the steps involved? Because they're the same intermediate, right?
Yeah, that's fair. Here, our carbocation was
Literally different.
actually the same
Well, yeah, but
because they were resonance forms of each other, but then they had to localize that charge in order to actually react. You're right that here, they are exactly the same, no difference. The difference is, will the energy of the bromide
yeah,
be enough to attack at the other position or to attack here?
and without heat, it's not.
Yeah, without heat, well, actually, without heat, it's not moving around a lot, and so the bromide physically stays closer to this. With heat, it has more motion as well.
In the thermodynamic control, it looks like, does the carbocation always happen at the most terminal carbon?
No, remember, it's an allylic cation, which means that it's the positive charge is both on atoms 1 and 3.
Okay.
And this is just an example diene. I can change the diene and make it entirely symmetric or quite different. What we're saying, though, is that the thermodynamic cation is the least stable, and the kinetic ion is the most stable. That's all. Thermodynamic, least stable. Intermediate. Transition state, rather. Least stable transition state. All right. I'm actually going to skip over the reactions with alcohols for a second because there is another reaction with conjugated dienes, and it's called the Diels-Alder reaction. Those of you in my lab, you ran this week. Those of you in the other labs, you're running this next week. The Diels-Alder is quite literally called 4+2 cycloaddition. There's two components. There is the conjugated diene, and the conjugated diene must have a specific orientation. I want you guys to take, for example, this conjugated diene. This is called 1,2-dimethylene cyclohexane. And then I want you to compare that to this conjugated diene. The orientation of the two pi bonds is different. On the left, our conjugated diene has the orientation of the alkenes cis to each other relative to the sigma bond that connects them. So we call this S-cis. Relative to the sigma bond, the dienes are cis to each other. On the right, relative to the sigma bond, our alkene is trans. S-trans. I think you'll agree that these alkenes are not always necessarily cis or trans. That's not a cis or trans alkene. That's not a cis or trans alkene. We're saying the two alkenes themselves are either cis relative to the sigma bond that relates them or trans.
S for sigma.
S for sigma. S-cis is reactive to Diels-Alder, and S-trans is not. So you'll never see us use an S-trans conjugated diene. We'll always use these S-cis conjugated dienes. And then we have dienophiles. And of course, a dienophile is something that likes a diene. We have two types of dienophiles. We have alkene dienophiles. And these alkenes typically have electron withdrawing group, an EWG. That is a group typically conjugated that pulls electrons towards itself, usually by having an electronegative atom. So that could be something like a nitrile is a good electron withdrawing group. A carbonyl is a good electron withdrawing group. Or we can see our dienophiles be alkynes. And actually, the alkynes also typically get these electron withdrawing groups. I'm not trying to suppose that a dienophile must have both a nitrile and a carbonyl. I just want you to see the two possibilities. Oftentimes, they'll have this. Now, without fail, the Diels-Alder reaction will always produce a cyclohexene template. And this is a mechanism we've seen. We actually practiced on this one. If you map your diene, carbons 1 through 4, and your dienophile 5 and 6, then you can always map over any changes that you want to make. So let me demonstrate with how this template applies to the reaction that goes to the left. You'll notice that in this template, I just have an alkene. And the alkene loses its pi bond in the product. 5 and 6 are no longer pi bonded. But in this example that I have on your diagram that goes to the left, I don't have an alkene, I have an alkyne. And the alkyne does not turn into an alkane. One of the pi bonds is consumed, but one of the pi bonds remains. And 5 and 6 both have these carbonyl groups coming off of them. So whether you use an alkene as your dienophile or an alkyne, there is a slight distinction. And the last thing I want to point out here is the stereochemistry. When it comes to Diels-Alder reactions, the stereochemistry can get quite intense. There's a lot of chiral carbons that can be formed, and the orientation of those chiral carbons can have a lot of different combinations. So you get the possibility of different structural and stereoisomers. We're going to keep it relatively simple. If you have a trans dienophile versus a cis dienophile, then you can predict that in your final product, you will either have trans orientation of those electron withdrawing groups or cis orientation of those electron withdrawing groups. the stereochemistry on the alkene impacts the stereochemistry in the final product. Oh, you know what? Oh, no, never mind. I see. So in this diagram, going to the right, that is the template. Going up is this example where I have a trans dienophile giving me a trans dicyano group. And going to the left is what happens when you use an alkyne. These reactions, in my opinion, are not hard, but they do take familiarity and practice. What questions can I answer about Diels-Alder?
Here, going up is to the
On the diagram, this is the reaction that goes up. That was
which is using a.
just highlighting the stereochemistry. That's what I'm highlighting there.
So on the temporal one, it loses 2 pi bonds
Yeah,
instead of just 1.
but it gains a ring.
Okay, so it's still.
Actually,
it loses
always.
1
I was
unsaturation.
gonna say, it looks like Diels-Alder always ends in a ring.
Well, it's called cycloaddition. So it should make a ring. And how big is that ring?
It's always Higgs.
4 plus 2. It's always 6. There are 3 pi bonds that are engaged in the reaction, but only 1 pi bond that results in the final product. 1 pi bond is consumed because it's addition, but 1 pi bond is converted into the ring, so it changes its degree of unsaturation from pi bond to ring.
Why is the one between 5 and 6 not a pi bond?
In the template,
No, in the product.
that is a pi bond. Remember I gave the template in black and I modified it in red.
Is it that red alkyne pi bond, is that what's consumed?
Actually, it doesn't really matter, but I said there are 2 pi bonds here.
Yeah. So
One of them is consumed.
to create the addition.
Mm-hmm. And if it's just an alkene, then there's only 1 to consume.
Start with 4 and with 3.
If you start with 4, 1, 2, 3, 4, end with 2.
Plus the ring.
Okay, plus the ring. Sorry, I thought you were saying pi bonds.
Sorry, degrees of unsaturation.
You're right. Reactions with alcohols. We can see we've got 5 of them. The first one I want to show you is acid catalyzed dehydration. This is the equilibrium reverse reaction of acid catalyzed hydration. It is the top middle, 12 o'clock. This is typically an E1 elimination. We're going to learn today that that means it has a carbocation intermediate. Because it's E1 with a carbocation intermediate, it's not Markovnikov because Markovnikov applies to addition. It is Zaitsev. It favors the Zaitsev alkene. What is the Zaitsev alkene? That's the most stable alkene, which typically means the most substituted. What I want you to notice about acid catalyzed dehydration, this is the only elimination with acid instead of base. We saw the synthesis of alkynes, and we needed strong bases. In a few minutes, we're going to look at the synthesis of alkenes. We will need strong bases. Why can't I introduce a base to try and run elimination on my alcohol? There's acid-base chemistry at play. If I introduce a base, will my base deprotonate a carbon, or will it deprotonate an oxygen? What's more acidic, a carbon with a hydrogen or an oxygen with a hydrogen? Yeah, our karyo trend says in the same row, the more electronegative atom is the more acidic. So introducing a base is just going to do acid-base chemistry between the alcohol. It's not going to do anything about stealing a beta hydrogen. So instead, what we need is acid. What the acid does is it gives us this protonated alcohol. Essentially, water bonded to the carbon structure. And then that water disassociates carbocation, intermediate. Now, what's the best acid on the carbon chain? The carbon. So now that we've formed a carbocation, we can run elimination. Some of the other things that we can do, I'll take us clockwise. We can convert alcohols to alkyl halides. This chemical thionyl chloride, SOCl2, well, of course, that's very good at making an alkyl chloride. But notice the stereochemistry. If the alcohol is wedged, then the new chloride is dashed. This inverts chirality. The same thing happens with phosphorus tribromide.
So something in an R configuration would turn to S.
Yeah, an R alcohol becomes an S alkyl halide. An S alcohol becomes an R alkyl halide. Those are two of the ways that I can convert to an alkyl halide, or I can use HX. But HX gives a carbocation intermediate and a racemic mixture. Notice how the reaction with HX doesn't give you a wedged halogen or a dashed halogen. The reaction with HX just gives you a flat bond. That's because whatever chirality the alcohol had disappears with the carbocation intermediate. And now the alkyl halide can form from either position. The last thing that I want you guys to be familiar with doing is taking this to a pseudo halide, not into an actual alkyl halide, but into a group that behaves like an alkyl halide. These are sulfonates, and the ones that we're going to work with is tosylate. In the organic synthesis lab, there are different types of tosylates. And the way you decide, or there's different types of sulfonates. The way you decide the sulfonate you want is sterics, electronics, solubility. On paper, they all do the same thing. So we're just going to use tosylate. I want you to notice what happens to the stereochemistry. This doesn't change the CO bond. If that alcohol was wedged, then the new tosylate group is wedged. What it's actually doing is swapping the OH for the OTS. And in case you guys are confused about what OTS looks like, I will draw out the structure of TS, and I think you will agree that it makes more sense to just draw it as TS. Paratoluene sulfonate. Paratoluene sulfonate, tosylate, is how we get that name. Toluene is a name for methylbenzene. And so you can see that the O of OTS was the O of the alcohol. That O never left. And in order to get OTS, the sulfonate, tosylate, has to have a leaving group, so we introduce TSCl. The Cl gets substituted by the O, and the H gets substituted by the TS. Those are our reactions with alcohols. Questions?
You're just ignoring the HX and PBr3.
No, we did them. Yeah, sorry. Those all three are conversions to alkyl halide. So they're just three different ways of getting there. Which alkyl halide do you want? And do you care about stereochemistry? In OChem 2, we come back to talk about alcohols a lot more. Okay. Last set of reactions. Reactions with alkyl halides and tosylate. Do you guys like my new ands? How else? I used to do my ands like this. I'm getting tired of them.
I think it's an ampersand.
You do a 3. Yeah, a backward. Oh, a 3 this way. No, that's a B.
Three with the line for line. No, this is a backward.
That's a B, you guys.
I don't do that.
I do it backwards. Yeah.
I think that does not look like an and. You're saying that doesn't look like an and to you?
I mean, what about an ampersand?
Kind of looks like.
That's what I was going for, but the ampersand is hard.
I do this line, which is a dollar sign. 3
And then
line.
start on the bottom.
Oh, I feel like respectfully we don't have time for this.
Yeah, you're right. Okay. When it comes to alkyl halides, I want you to consider their substitution. The substitution of an alkyl halide dictates the reactivity of the alkyl halide. If an alkyl halide has low substitution, what would those be? That would be a methyl halide, a primary alkyl halide. Those alkyl halides have very poor carbocation stability. These are high energy carbocations. But the more substituted the alkyl halide, the more stable the carbocations that can form. Secondary carbocations tertiary carbocations. Those are the most stable that we can form. So as we move from left to right, we see increasing carbocation stability, which means some alkyl halides may react by a carbocation intermediate. And it's more likely that it's the more substituted alkyl halides that react by a carbocation intermediate. But on the left, we have very little steric strain. There are no neighboring groups on that methyl halide, but when you get to a tertiary alkyl halide, you've got all of this steric strain surrounding that carbon. So this is increasing sterics. Who cares? What's the problem if an alkyl halide has a bunch of groups around it? Well, remember that all those groups are magnets, and the alkyl halide carbon is an electrophile. It's a partial positive carbon. So that carbon can accept electrons from a nucleophile. If you want to get a nucleophile to that carbon, you're going to have to push against all of those neighboring groups. You're going to have to push their magnetic repulsion away so that a nucleophile can access that carbon.
So
Very hard to do.
less reactive, more stable, higher activation energy.
Depends on the mechanism. It depends on how it's reacting. For a methyl halide, where there is no strain, a nucleophile pops right onto that carbon. It doesn't have to fight against anything because those hydrogens aren't hard to push away. But on a tertiary alkyl halide, a nucleophile tries to get close and rarely has the energy to actually repel the other groups to access the carbon. You guys are thinking about magnets in your heads right now, aren't you? I hope you are. And I want you to think about having a magnet that you can just get right up to and do a reaction with. There's no strain. And then I want you to think of a magnet that you are trying to get to, but the closer you get, the more repulsion you feel from all these other groups. And it's really hard to get that magnet close to the reactive spot. Alkyl halides with low substitution prefer mechanisms that avoid carbocations and do direct substitution. But highly substituted alkyl halides prefer reactions that involve carbocations because they can stabilize them, and avoid reactions that try to involve any direct substitution. So we've got this table here, and it says competition between substitution and elimination. When it comes to reacting with alkyl halides, a nucleophile might act as a nucleophile and do substitution, but a nucleophile might also act as a base and do elimination. But not everything is good at being a base. Not everything is good at being a nucleophile. And so we have 4 categories. We have strong base, strong nuke. All of the reagents that I'm going to expect you to know are there at the bottom of the page. And I'm going to organize them here now. Hydroxide, alkoxide, like meth oxide, eth oxide. Those are both good at taking hydrogens and good at bonding to carbon. They are strong nucleophiles and strong bases. So are carbons that hold a negative charge. Carbons that hold a negative charge are very good bases. They're also very good at bonding to things. Things that are, I realize I wrote base on the wrong side over there. Things that are good at being bases, but bad at being nucleophiles. The one reagent that I want you guys to think of here is just tert butoxide. This is the only one for now that we're going to work with. Yes? We're talking about the 4 categories. Do you see how we've already addressed the column? The column is substitution. And so depending on the substitution of the alkyl halide, you're going to find yourself on one of these rows. Depending on the reagent you mix it with, you're going to find the cross column. What we're doing, though, is taking the reagents at the bottom of the page, and we're saying what categories do they fit into. Sure. No, just categories. We're going to talk about what competitions occur in there. Why is this a good base? Well, it's exactly the same as hydroxide and alkoxide. It's just a negatively charged oxygen. Why is it a bad nucleophile? To be a base, all you have to do is reach out and grab a hydrogen and go away. But to be a nucleophile, you have to form a bond, donate electrons, and then stick around. And tert butoxide is big and bulky, meaning tert butoxide brings with it a ton of steric strain. So it's hard for tert butoxide to get in there and be a nucleophile and make a bond because it is so sterically strained. It's a bad nucleophile for that reason. And in terms of being a base, because it's so bulky, these bases are Zaitsev bases. They go for the most substituted alkene, the most stable alkene. But tert butoxide is the anti-Zaitsev base. It's bulky, so it goes for the least substituted hydrogen. It gives the least substituted alkene. Our last 2 categories, things that are good at being nucleophiles but bad at being bases, and things that are bad at being everything. Those things that are still good at being nucleophiles but are not prone to taking hydrogens. Those are things like cyanide and azide and bromide, iodide, and sulfides. You might remember that sulfur is a better acid than oxygen because atoms in the same family become better acids the larger they are. And so sulfur is a worse base than oxygen, which is why we say sulfur is a weak base, whereas oxygen in that same bonding environment, a strong base. Better acid, weaker base. Things that are bad at being nucleophiles and bases, we've got chloride, but predominantly water and alcohols like methanol, ethanol, all of our other alcohols. To be honest, the ones that you're going to see the most often here are water and alcohol. What I've done with the middle of our worksheet, this table is something that I always have students fill out, but I've converted the table, or like what information the table gives, into the reaction diagrams that you've been getting familiar with. So I'm going to fill in the information for the table, and I want you to spend time later addressing how the material in the table is transformed into the reaction diagrams that you see below. two different ways to approach what happens. All right, on the left-hand side of our table, we have the degree of substitution of our alkyl halide. On the top, we have what type of reagent we're dealing with. And I apologize, sometimes I put poor instead of weak. So P instead of N. Weak base, strong nuke, weak base, weak nuke. Methyl halides cannot undergo elimination. Let me say that again without studying. Studying, I said, but I meant stuttering. Methyl halides cannot undergo elimination. Why? There's only one carbon. Methyl halides are not good at forming carbocations. So methyl halides only substitute, and they substitute by a second-order mechanism. Regardless of what the nucleophile is, it substitutes by SN2. What did we learn about SN2 yesterday? It means second-order nucleophilic substitution. Nope. We didn't say that. There does have to be a nucleophile present. Otherwise, it can't be nucleophilic substitution.
What is second-order nucleophilic substitution?
Great. That is exactly what I just asked. What did we learn yesterday that second-order nucleophilic substitution means?
It involves both of the reagents.
Two reagents are involved at the rate-determining step. And another way that I would say this, strong magnets are interacting. Well, things that I call weak, I would say you should think of those as weak magnets. So then why are weak magnets being drawn to react all at once the way that strong magnets do?
Because isn't it, well, when we talked about SN2, we talked about like the rate determining step.
Mm-hmm.
We talked about with that being two reactions, it's dependent on the quantity of each, and then the more you have of each, the faster the reaction goes.
That is the rate, but not the mechanism. The mechanism is what says the rate is dependent on both of them. The reason that whether the nucleophile is strong or weak, the reason that it all reacts in one step is because the only other way to substitute would be have the leaving group leave and create a carbocation, and then have the nucleophile bond to the carbocation. But carbocations are really hard to form on methyl carbons. So it takes less energy for even a weak magnet to be drawn in and substitute the halide than to go through a carbocation intermediate. Primary alkyl halides, still not very good at forming carbocations. So when they can, they do SN2. And when they can't do SN2, they're usually split with another reaction. For instance, our big bulky base at a primary carbon starts to feel uncomfortable because of the sterics of that primary carbon and its own steric strain. So a big bulky base might substitute at a primary carbon. It might eliminate at a primary carbon. But all of these other groups run SN2. At a secondary alkyl halide, our strong base, strong nucleophile is starting to feel steric strain. The substitution becomes harder for it to do because there's increasing sterics. So sometimes it runs elimination. The energy difference between running substitution and elimination becomes comparable here. So there's competition. Whereas now, our big bulky base would never be expected to run substitution, just elimination. Things that are bad at being bases, they're still running SN2. But things that are not good at being nucleophiles, they're not strong enough magnets to come in there and kick off the leaving group. They're also not good bases, so they're not good at coming in here and grabbing a hydrogen. These will wait for a carbocation to form. Then, once the carbocation is formed, they'll either substitute or eliminate. Our last row, the tertiary alkyl halide. Things that are good at being bases, eliminate. The sterics are far too high for SN2. To have a nucleophile approach that tertiary carbon, it will feel too much repulsion from all those other groups, and it cannot directly substitute. So if it's good at being a base, it runs elimination. If it's not good at doing anything, it waits for a carbocation. And this last box, if you look at your diagrams, you'll actually find that this is not common. Things that are bad at being bases and good at being nucleophiles, they can't be nucleophiles. And they're not good at being bases, so we don't use them in these conditions. Here's a takeaway I want you to have. At a tertiary alkyl halide, SN2 is forbidden. Oh, I forbid you. Which is a silly way of saying that it's just too high energy. Something else will happen before you get to the energy that SN2 requires. Yes? Mm-hmm.
See SN2, you see two reagents are involved in nucleophilic step. And then what is E2? You said that's elimination?
Yep.
How does that vary from E1?
E1 has a carbocation intermediate. SN1 has a carbocation intermediate because the rate determining step involves one molecule dissociating into a carbocation. One molecule, SN1.
How does E2 vary from E1?
E1, carbocation intermediate. E2, no carbocation.
So anytime there's E1, SN1, you already know there's a carbocation.
Always. If it's E1, SN1, E1 or SN1, the first order rate is telling you there's a carbocation intermediate. Let's talk about these examples where there is competition, where two molecules can run into each other in different ways at roughly the same energy and lead to different things. Like sometimes I get home and I'm snacky, so I have a Pop-Tart. Other times I get home and I'm snacky, so I fry up the potato peels while I'm making dinner. Those are very different ways of consuming food. And I feel like my analogy there is actually not great.
You actually do that?
Yeah,
Is that good?
I did that last night.
I've never done that.
I skin the potatoes before I cook them, and then I fry them. Anyways, if there is a competition, russets, then you can typically use temperature to control which reaction is favored. So low temperature, and we'll typically write this as low T, promotes substitution. Whether we're trying to promote SN2 against a competition with E2, or whether we're trying to promote SN1 against a competition with E1. If we run the reaction at lower temperature, we're more likely to run substitution. Heat promotes elimination. So on the next page, on the last page where it actually asks you about predicting the products from some of these, you'll notice that in some cases it says, let's take a look at the right side second from the top we have what type of alkyl halide? I'll draw this up so that you guys can follow it too. What type of alkyl halide? Methyl, primary, secondary, tertiary? It's a tertiary alkyl halide. What type of reagent are we reacting it with here? Good, looks like water. Which falls into the category of not good at taking hydrogens, not good at substituting groups. It's a weak magnet. Exactly. And how is temperature controlled? It's not specified. So we should expect two different products. We should anticipate that this will both eliminate the alkyl halide by a carbocation intermediate, and that it will substitute the alkyl halide by a carbocation intermediate. When it does elimination, it forms the most stable alkene that it can. Which of the beta carbons is the most stable for the alkene to form on? Good. The most substituted beta carbon leads to the most substituted alkene. So this beta carbon runs elimination, or is part of the elimination. I form my alkene between the two tertiary carbons. If I run substitution, do I have any risk of a carbocation rearrangement after the carbocation forms? The carbocation would form wherever the leaving group is.
So in that tertiary carbon.
That's a tertiary carbocation. That's not going to rearrange. But what does my final product look like when water is the nucleophile? Is it just water bonded to the structure? It becomes an alcohol. I want you guys to remember, back in our alkene addition reactions, we said that water is a precursor to alcohols, and alcohols are precursors to ethers. When we did the halohydrin addition, we were left with an alcohol. When we did the haloether addition, we were left with an ether. It's the same thing here in substitution. Alcohol in a reaction will form an ether, and water in a reaction will form an alcohol.
I guess it doesn't really matter too much, but in a substitution reaction like this, with that OH group,
Mm-hmm.
we have to show two products, and one with bold coming at us and one with dashed line.
Right, so on this sheet, oh, actually that's an achiral center.
Okay.
So it doesn't form wedge and dash. There's only one configuration. On this sheet, if you do form a mixture of products, you should predict a mixture of products. If you notice the reaction right above it, it says H2O and heat. So that's going to promote an elimination. Good. All right, I'm going to post an answer key for this. I'm also just going to quickly mention that there is a multi-step synthesis challenge at the bottom, where instead of a roadmap, I also am going to make another roadmap. A roadmap that incorporates alkenes, alkynes, alcohols, and alkyl halides. A roadmap that is similar to what you might come across on the final. I'll post an answer key to this. I'll post that roadmap and the answer key to it. And I'll post the answer key here. This is all in words, so it challenges you on your nomenclature. You've got to be able to draw the structures. And then it doesn't tell you how many steps are needed. So it's a process of knowing what functional groups do you have, what reactions can they undergo, what new functional groups can they make, and how many steps do I need to get to that final product. Yes?
I was like, how are we going from methane?
Yes, the goal is methane to methanol. What reactions do you have to do to go from methane to methanol?
Make an OH group
That's right. So let's look at mechanisms, shall we? We're going to spend our last 10 minutes doing mechanisms, okay?
So is that all the material for the class? It's just review now and
Yeah.
covered it?
No, the mechanisms would be the last of it.
Mechanism.
Yep. Once I finish the mechanisms, that is all the material. I've shorted you on nothing but your time.
Is this the mechanisms?
Yes.
Okay.
Yes. How long is a first order mechanism? Several steps. How long is a second order mechanism?
Several.
Second order?
Well, it should be only 1 or 2 steps.
Are you looking at the same sheet that I'm looking at?
Well, I thought it was 1 the first time when you said several, so.
First order is how many steps?
1.
First order,
Oh.
2.
2.
upwards of 2. Yeah, with the possibility of rearrangements and some deprotonations.
3 for the second.
How many steps is a second order mechanism?
1.
Okay. So what's easier to draw? A first order mechanism or a second order mechanism? Second order is way easier.
Is that because they both happen at the same time?
Second order means the nucleophile and the electrophile are both involved in the change at the same time. First order means one molecule is involved.
At a time.
Well, yeah, not really just at a time, but one molecule is involved in the highest energy step. So the slowest part of the reaction involves just one molecule, which means you're going to need more time. I want you to compare first order substitution, SN1, and first order elimination, E1. Notice how they start exactly the same, carbocation forms. The beginning of a first order mechanism does not differentiate between elimination or substitution. Then there's that possibility of a rearrangement. Do you guys remember why I'm calling this 1A? Because it doesn't always rearrange. If there's a carbocation, you need to look for the rearrangement, but if it doesn't rearrange, don't show it rearranging. Then step 2, if it's elimination, the second step is steal the hydrogen, do a deprotonation. But if it's substitution, then sometimes we have to follow that up with removing a hydrogen from whatever the nucleophile was. Here, we had to remove a hydrogen from water. So there is a necessary deprotonation step. But sometimes the nucleophile doesn't need to be deprotonated. Chloride is gone. Chloride doesn't need to be deprotonated. Thank you, Rowan. Second order elimination, 1 step. Second order substitution, 1 step. But sometimes a second order, like on a methyl carbon, it does still require a subsequent deprotonation, sometimes. So let's go through one of these. I think we only have time for SN1 or E1. Which one would you like to see? SN1, okay. What reagent is needed over the arrow to complete my SN1 mechanism? Good. Why do I want CH3OH and not CH3O-? If you remember from our table, we said CH3O- is a strong base, strong nucleophile. And on a secondary alkyl halide, a strong base, strong nucleophile does SN2 or E2.
Not SN.
How do we know that this is SN1 other than the fact that it's under the header SN1? It loses chirality at the substituted carbon. There's a carbocation intermediate, chirality is gone. If it were SN2, it would actually go through a backside attack. And you can see that on the SN2 below, inversion of stereochemistry. So we need methanol. We cannot use methoxide. Okay, you guys have seen how these can be done step by step. I'm going to show these fully sequentially, meaning each structure is just going to feed into the next.
So does SN1 always get rid of the chirality on the substituted group?
Yeah, SN1 always removes our chirality. I'm going to draw both of my reagents, but the first step only includes the leaving group leaving. The bromide getting kicked off. That carbocation is achiral. It's sp2. It's trigonal planar. It's achiral. So there is no more wedge or dash. Do I need to consider a potential rearrangement? Secondary carbocation surrounded by secondary carbons. No benefit in rearrangement. No rearrangement occurs. So we skip carbocation rearrangement, and we go down to step 2, nucleophilic attack. My oxygen acts as a nucleophile. It can add wedged. It can add dashed. It's going to create diastereomers. And since that chirality doesn't really matter, we can draw that as a flat line.
I see, that's why. Not because there isn't just one configuration, it just doesn't matter.
Not because it's only wedged or dashed. The reason we draw it flat is because it's both wedged and dashed. It has lost absolute configuration. It's now in a mixture.
So like on an exam, if there's something like this that appeared and we decided to draw both configurations, would that also be okay?
Yes, drawing both diastereomers is good. Okay, here's my last step. In order to make that ether, I have to deprotonate. By the way, did you remember? Since we reacted the alkyl halide with an alcohol, we formed an ether. Alcohols are the precursor to ethers. Would you like to see SN2 or E2? Do you know what? I have enough time that I can show you both the SN2 and the E2 mechanism, because they're both just one step. I wonder if you can answer this for me. What reagent is needed over the reaction arrow for the SN2? If we had HCN, which is cyanic acid or hydrogen cyanide, it wouldn't be the same as CN minus. But if we wanted it to be CN minus and we wanted to balance it, we could say NaCN, KCN, or we could really just put CN minus. But HCN is going to make acidic conditions. It's going to change things a little bit.
So we want either KCN or CN minus?
Yeah. Yeah, either or. The reason that I can ignore K is because it's a spectator ion. Here's my mechanism. Are you ready? Done. Easy. And then for the elimination mechanism, do you guys remember that that term I introduced back in section 6, right after the midterm, anti-periplanar? E2 elimination requires that the leaving group and the hydrogen be anti to each other. One up, one down. And here is that up leaving group and a down beta hydrogen. The reagent that I could put in here, I could show something like hydroxide with heat, methoxide with heat. But I can't show this as tert butoxide because tert butoxide is an anti-Zaitsev elimination base. Tert butoxide would go to the wrong position. Hydroxide bonds to my beta hydrogen, acts as a base. The CH bond forms my alkene, and my leaving group leaves. All at the same time. The difference between E2 and E1, E1 forms a carbocation and then forms the alkene. E2 does not form a carbocation.
In the second order substitution, do we have just Cl just floating?
Yes, Cl minus is a byproduct. Thank you.
OTS would be a byproduct from the second.
OTS and H2O, since I chose hydroxide as my base. Thank you for calling attention to that, Gavin.
But we wouldn't need.
Usually the focus is on the major organic product. I've taken you over, but I'm also cutting you short. We've covered everything. That is all of OCHEM 1. Congratulations.
A little early to congratulate.
Well, it's my last chance to congratulate you. It's been a pleasure having you guys in class. It's really been a great semester. There will be practice materials, like a roadmap for next week. But I also encourage you to bring in practice exams and work on them while Natalie is here to answer questions, to go over things with you.
So we actually don't need to watch lectures unless we're unclear on.
Correct. I still am going to send some recommended lectures to watch. That might help clarify some of the concepts that we breezed right over.
But we didn't technically miss any lectures.
No, I didn't cut you short on anything.
Cool.
We're done.
Lock it in.
We just are missing the practice time.
Yeah.
So more practice. Keep practicing. Spend time. I can't say this enough. You've got 2 weeks until your final. Spend so much time prepping. If you want to do well on the final, spend so much time studying. Go through the practice finals. Rewrite your notes. Make your cheat sheet a whole bunch of times. Know that thing front and back.
Is the final longer than the midterm? Like
The final is longer than the midterm. It's more questions and more points.
sick.
Can you tell us how many questions?
It's all on the
Yeah, it's usually like 30 some.
Oh, that's not bad.
It is 30 multiple choice, and then like 10 short answer.
And then you always have like some bonus at the end.
Always bonus questions. Yeah, look through the practice finals. That's going to be the best for you.
Finals at 11?
The final exam is here at 11:20 on August 6th, Thursday, August 6th. If there's a reason that you can't make it, make sure you email me. Okay,
Thank you.
take care, guys.
It's been a good semester.
It's been a great semester.